Welcome back, and thank you for joining me for Physical Sciences for Year 10 for the Australian curriculum. In this explanatory video, we're going to be looking at the concept of unusable or wasted energy. We're also going to be looking at the idea of how we work out energy efficiency, and I will explain to you how you use energy efficiency or use how to calculate it, and then also how to produce Sankey diagrams and interpret Sankey diagrams. Okay, so let's just define what unusable energy is. Basically, we know that due to the law of conservation of energy, the energy we put in is the energy that we put out. Okay, now as we've stated many times, machines basically convert energy from one form into the next. So not all of the energy is transformed into the usable energy that we want. Let's take our car. You put chemical potential energy into the car. That's great, petrol. What do we want out of it? What's the fundamental energy that we want out of a car? It's kinetic energy, because we want it to move us from one place to the next. Forget about the stereo, forget about the AC, forget about all the paraphernalia around the car. The job of a car is to move it from A to B. Move it. So kinetic energy. Unfortunately, most of the energy can be lost in the form of sound and heat. So we don't have a huge amount of efficiency of the internal combustion engine converting chemical energy into kinetic energy. It may only be 65%. So that means that the efficiency rating of the car is not very good, which means that there's a lot of wasted energy or unusable energy. So that's what we mean. Now, we deal with energy efficiency all the time, and energy efficiency is big business. You look at any appliance that you buy, and it will have an energy efficiency rating. And this basically says how well or how good it is at taking your initial energy right at the beginning and converting it into the energy that you want. The better the efficiency rating, the better it goes from the energy in to the usable energy out. So let's look at an example. Let's look at this girl here. She's going for a run. Now, when she goes for a run, she is using chemical energy. So chemical energy is what she's put inside her body in the form of food. She'll have her carbohydrates, her fats, and her proteins. She puts it into her body, and then she uses her muscles, and really what she wants out of it, the main thing she wants out of it, is kinetic energy. However, some of that chemical energy will be converted into heat. So she will have lost some of that energy in the form of heat, and as a result, she will only be able to go so far with her kinetic energy. She will only be able to run so fast. You look at 100 meters, basically Usain Bolt can only go at a certain speed. You can't go any faster than, I think it's around about, 9.7 seconds for 100 meters. Okay, there's going to be a huge amount of heat which is lost. Now, if the body was more efficient, we might be able to cut down the amount of heat loss and put it into kinetic energy. And our efficiency of our biochemical systems will allow us to convert more chemical energy into kinetic energy. That's down to evolution. However, when we're talking about machinery, that is down to a man-made concept. So we can actually change and improve upon the machines that we've got. So let's look at a very simple machine. Here's a simple machine. It's a light bulb. Okay, light bulb designed by Thomas Edison. Basically, you've got a filament and you've got electricity flowing through. So our in energy is going to be electricity. What do we want a light bulb to do? We want it to generate light. Great, but we're going to be paying for the electricity to generate that light. Now, what you want is the light. However, what we get from a lot of light bulbs, and if you don't believe me, go and put your hand carefully up against a light bulb, you'll see that there is also heat. Now that heat is wasted, but it comes from the electricity. We've got transformation of electricity into heat. We've got transformation of electricity into light. We want to make that light bulb as efficient as possible. So when you're doing your transformation diagrams, when you're putting together the different types of energies, you have got to put into those diagrams the energy which is wasted. By knowing the amount of energy which is wasted and then the amount of energy which is useful, you can then work out the efficiency rating of a car. of a machine. Okay, well, let's take another scenario. Let's look at this diagram that we've got here. This diagram basically is what we call a Sankey diagram. Now, Sankey diagram, it's a funny word, but basically it shows in what direction all the various energies go. Now, if you look at this, what we're looking at is fossil fuels going into power stations, which are then going to generate electrical energy. Now, the fossil fuel, the coal, okay, is basically stored chemical energy. Now, that has come initially from the sun. Okay, the sun has allowed the plant to photosynthesize, the plant has died, and then that stored energy is being converted into chemical potential energy. Okay, so what then happens is we dig up the coal, we take that coal and we burn it. We burn the coal and we generate electricity. And the electricity is the useful energy that we want. Now you can see that from the total amount of solar energy, most of it is lost. Most of that solar energy is lost in the form of light and heat. Hence you've got a really big arrow. Now the size of the arrow demonstrates the amount of energy which is lost. When that energy is first trapped by the plant then uses that energy for its own purposes because it's got to live. So it uses that energy to make food, and then it uses that food to grow. So it will lose some of that energy that was trapped from the sun. So then we've got that energy that the plant dies, and that energy that's in that plant is then stored, it's trapped. Okay, so what we then get is over millions and millions of years, the coal is reformed. So there's going to be breakdown of the plant material by bacteria. So we've got more energy which is going to be lost from that breakdown of fuel. Remember, that's the energy lost from the sunshine. We then dig up the coal. Okay, so the coal comes out and we've got this lump of fossilized energy, and we burn it. So when we burn it to heat water, to produce steam, to produce kinetic energy. When we burn it, some of the energy which is trapped inside that coal is lost as heat up through the chimneys. Hence you've got that wasted heat. So some of that energy has been wasted. Now what you should have noticed now is that the arrow that we started with, the thick solar energy that we've got, has been whittled away, losing little bits each time, until eventually some of that heat is converted into steam. The steam drives a turbine, drives a magnet inside a coil of wires, which generates our electricity. Our electrical energy there is our useful energy. Now we can put numbers along this side if we know the percentages of the energy that comes through. Now we know that if you look on the left hand side, we get 100% of energy coming from the sun. Well, that's our closed system. So all of our energy comes from the sun, so that's 100%. And these are arbitrary units, but 55% of it is lost before it even hits our planet. Then we've got some of the energy which actually hits the planet, as we say, is used and trapped by plants. We then lose some of that energy again, so maybe 15% of the total amount is lost. So we've lost 55% because it doesn't even hit the planet. We then lose another 15% from the plants using the energy. We then use another 15% of energy which is lost in the formation of coal. We then dig the coal up and we lose another 5% of the total amount of energy that the sun produced from burning the coal, which leaves us only maybe 10% left over. Now, these percentages are really, really high, but they're nice numbers to deal with. The value is a lot lower, okay? But what I want you to be able to do is to look at these figures and be able to interpret what is going on, okay? So each figure looks at the amount of energy which is lost. Now, in a moment, I will use the Sankey diagram to show you how we can calculate the energies. Now, these energies can be in percentages or it can be in joules, so it depends on what we're dealing with. So from this, what we gather is that 10% of the total amount of sun's energy from this diagram is basically going to be converted into usable electricity. That means that we've got 90% of the energy is wasted. It's lost. It's not very efficient, as we can see. So as I stated in that last statement at the bottom, what we are trying to do and what we need to do as mankind, as a human race, is try and improve the efficiency of using that sun's energy if we're going to go down that path. We need to try and get, instead of 10% coming out, wouldn't it be great if we had 90% of the sun's energy being converted straight to electrical energy? That would be fantastic. Actually, if we could only change it so there's an extra 1%, that would be a huge step forward. Okay, so what I'd like you to do, there's a couple of questions on Sankey diagrams on exercise 3.1 in your iBook, which you can basically have a go at the end of this video. So we've talked about Sankey diagrams, we've talked about useful energy and wasted energy, and I've talked a lot about energy efficiency. But how do we calculate energy efficiency? Now, energy efficiency is written as a percentage. Now, the percentage basically is of the total amount of energy coming into the system, how much of it is going to be converted into useful energy. And the formula that we use can be shown there in bold. Efficiency as a percentage equals the useful energy, the amount of energy coming out, times 100 divided by the total amount of energy put in. And from that you will get a value. Now, you need to be able to calculate the efficiency percentage, or you might be required to convert it so that we can work out the amount of energy output or the total energy input. Now, there's a variety of different scenarios in the iBook which we'll run through. I'll go through a very simple one here. Now, just to recap, down at the bottom there you've got an energy rating sticker. Now, you'll see this in a lot of your appliances. You see there's 5 stars. The 5 stars basically indicate, if you get that red line going all the way up to the 5th star, it's 100% efficient at converting energy from its input to its output. That ain't going to happen. But the closer we can get to those 5 stars, the better your appliance is converting it into useful energy. In this case, 3.5 stars basically means it's about 75% efficient at producing that energy, and all appliances will have this on there so that you can make an informed decision. Okay, well, let's have a look at a little example. So we've got an example here of a Sankey diagram which is showing the amount of energy which goes through from a light bulb. So we've got 240 joules of electricity coming in. From this, 48 joules of it is heat and 192 joules of it comes off in light. Now, remember, it's a light bulb. What do we want the light bulb to be able to do? Generate light. So we're looking at the efficiency of the light bulb. How good is the light bulb at producing our usable energy, which is light? So 192 joules is useful, 48 joules is wasted. So how do we work out the percentage of that 192 joules from what we started with? Well, we use our equation. Our useful energy is 192 joules. Our total energy is 240 joules. So we substitute that into the equation and we do 192 times 100, and then we divide the whole lot by 240. Now, on your calculator it's really simple, because you just put in 192 times 100, divide 240, and then hit the equal sign. Okay, from that we'll get 80% efficient. So it's a really good light bulb. That's a really good light bulb if we've got 80% efficiency. Okay, so what I'd like you to do is have a go at trying the exercises from 3.2 from the iBook, which will give you some more examples of using these types of equations so that you can work out the efficiency rating. Also, check out some of the questions that I'll put on the pop quiz later on in the course, and they'll give you some good practice. Okay, well, I hope you found that useful, and join me again for our next bit of insight. We're going to be looking at hydroelectric power. So thank you for watching.